Got it? Okay. Dear Father, we thank you for this day. I thank you again for these students. Just be with us today. Help us to just try to draw together our thinking on Chapter 11 and just encourage these students just to do their best each and every day, Lord, for your glory. We never pray, Lord Jesus. Amen. Again, sorry I'm starting so late. I really tried to start earlier in here. I just thought it was important for me to finish grading your quiz before I did anything else. Evan? Tyler? Francisco? Min? Cameron? Let's see here. Sarah? Devin? Brett? Taylor? John? Brian? Jordan? Sean? Sean does not exist. Let's see here. Thomas? Seth? Will? Braden? That everybody who's here who took the quiz have the quiz? Hopefully. All right, so first order of business today, since I think there are very few of you who will be bored by seeing this, is to go through the solution here. Now, this quiz, all right, was, I said, problem one, I said, find if the sequences below converge. If they converge, also find the value of their limit, right? And notice that you don't have to show work here. So I'm just grading the answer. I didn't get partial credit. If you're wrong, you're wrong. Sorry about that. So that said, I'm going to pretend as if those instructions were given differently. I'm going to justify each one, okay? But you should understand that if you think about it, just kind of set aside my answers here for a second. Ask yourself the question, how could I find that without writing all this down too, right? Because that's all you had to do. If you could write down the right answer here, I would have given you full credit. That said, we are after something more also, right? So let's justify. So A, 2n plus, 2 plus n, right? Plus n squared divided by n plus 7 quantity squared. So what do you do here? We just do algebra. 2 plus n squared divided by n squared plus 14n plus 49. Now, of course, technically speaking, I could have just divided the top and the bottom by n squared to start with, but I think this is easier for you guys to follow, so I'm doing this. Now, what's my next step? This is 2 over n squared plus 1 over n plus 1 divided by 1 plus 14 over n plus 49 over n squared, right? And this goes to 0 plus 0 plus 1 over 1 plus 0 plus 0, which is equal to 1 as n goes to infinity, all right? So, therefore, the limit as n goes to infinity of 2 plus n squared divided by n plus 7 quantity squared is equal to 1. We can say this. We can say, or in other words, that is, A sub n converges to 1. Where A sub n is what? I'm tired of writing these formulas. Okay. Doing some name calling here, if you don't mind. Okay? Any questions about this one? I think a lot of you got this one right. Many of you, of the points you got, this is one of them, right? Yeah. Just a little word of warning. Some of you are saying, I don't think just one person, a few people are saying a sub n converges on 1, or it's getting close to 1. This is not good terminology. The limit is equal to 1, right? The terms in the sequence are getting close to 1, that's true. But the limit itself, the limiting value, is 1, all right? Not close to 1, not approaching 1, it's 1. Okay, there's a difference between a sub n and L. L is equal to 1. A sub n is approaching 1. You should be careful not to confuse those two things. B. No, this was a trap. I'll keep using a sub n as a label. N squared times the sine of n pi. What did I say at the start of this problem? Sequence, right? What's a sequence? A sequence is a function from the natural numbers to some set, in this case real numbers. What's the sine of n pi? No. What is the sine of any? Look. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. You get the idea? This is always 0. Right? So this is just a very sneaky way of telling you a sub n is equal to 0. It doesn't matter that n squared is getting huge. It is always killed by 0. Not something that's limiting to 0, but something that is just 0. So there's no need for anything here except for just to say this is nothing more than the constant sequence. Constant sequence 0 stays 0. So of course, thus, I'm tired of writing limit, thus a sub n goes to 0. It's a sequence. That's the first thing we said, is a sequence is a function from the natural numbers to a set. So yeah, it's always going to be a whole number. Let's see here, C. Yeah, it's kind of like, you got to know where you are, right? I mean, so first thing is context, and sequences, and that's the dangerous thing about extending n to be a continuous variable, right? It's one of the dangerous things about that. So this one converges to 0, right? A sub n converges to 0. C. Here we have a sub n is the cosine of twice the inverse tangent of n, minus n rather. So let's do this in stages. Curses. It's getting away from me. Here you go. Oh, wait a minute. Which one did I give you? Oh, no. Did you take this quiz? Did you take quiz 2?
No, not yet.
Oh, you didn't take it. Okay. That's why I'm confused. Oh, now I'm very, okay. Okay. All right. So, work your way inside out here with a composite function, start inside, work out, right? So notice that inverse tangent of minus n, right, is just equal to minus inverse tangent of n because inverse tangent's odd. But this goes to minus pi over 2 as n goes to infinity, because the graph of inverse tangent looks like what? It's the graph of tangent between plus or minus pi over 2 turn sideways, right? This is y equals tangent inverse of x. So therefore, tangent inverse of x goes to pi over 2 as x goes to infinity. So therefore, inverse tangent of n likewise goes to pi over 2 as n goes to infinity. I'm using the continuous extension theorem, I suppose. Or just common sense, whatever you want. Anyway, the point is this tangent of inverse tangent of minus n goes to minus pi over 2, right? So thus, a sub n is going to, well, let me see here. Let me use some notation here. So the limit as n goes to infinity, right, of the cosine of twice the inverse tangent of minus n is equal to the cosine of the limit. Now, how do I know this? Right, the composition of continuous. Oh, what did I call this stupid thing? The composite sequences theorem, right? Cosine is continuous. I can do this because cosine. Where is cosine continuous? On the whole real line, right? And we also have that 2 times the inverse tangent of minus n is converging to what? Looks like minus pi, right? In other words, this is a convergent sequence. I'm feeding a convergent sequence into a continuous function. I can use the composite sequence theorem, which says this, and then, of course, that's cosine of minus pi. What's cosine of minus pi? Minus 1. And there you have it. Now, to just find this limit, do you have to do all this stuff? Certainly not, right? To find the first limit, what could you do? What's a way to, cheat a math problem and not think that hard if you just want to find things? There's a 90% chance, roughly speaking, unless I had a lot of time. If I had a lot of time, maybe I could construct problems that would foil this method of inquiry. But honestly, folks, and don't ever write this down on your test because it doesn't count for anything. But if you plug in 1,000, you can pretty well tell what's going to happen, right? If you plug in 1,000 into this formula, you're going to get something that's like 1,000,000 plus change divided by 1,000,000 plus change. You'll get basically something that's very close to 1. Odds are the limit's 1. Here, if you plug in any number, you'll get 0. That's a clue, right? Here, if you plug in 100, you'll get something that's probably pretty close to minus 1. So if you want to check your work, right, if you have time, or if you're uncertain of how it should go, right, you have calculators, right? You can plug in values and see what it's tending to. But you can't spend all your time on that, right? So the more you know, the less you have to do of that, the better. Right? So this one, personally, the way I look at it is like inverse tangent. I know what inverse tangent is, right? I'm not learning that on the test. I already know that. I know that inverse tangent has a graph that looks like that. I know it goes to pi over 2 as x goes to infinity. That's not something I'm figuring out on the test. Quiz, whatever. And I know, what I can do with the minus and such. But if you don't know all those things, of course, a natural defense against what you don't know is to use what you do have in your hand, which is a calculator. You could paper over a lot of things that you don't know with that if you know how to use it responsibly, right? Now, if you put on your quiz that if I plug in 1, if I plug in 100, if I plug in 1,000,000, I get these numbers are getting closer and closer, so the limit's approximately blah, I'm really not going to give you much credit for that. I want to know what the actual limiting value is. I want a 1 or a minus 1 or a 0, whatever it is. Not 0.99, not 1.01, minus 1.1, whatever. Does that make sense? No. But, I mean, I'm almost reluctant to tell you that. I almost don't want to tell you that because I don't want you to sit there and plug numbers into your calculator the whole time. But if you're so lost that you're just looking for some branch to hang on to start climbing the tree, goodness gracious, plugging numbers into a calculator is at least something, right? That gets you somewhere. Not the end of the road, but something. How about this, D? Here we've got x to the n over n factorial. Now this is basically a section. I think this was an one of the fun facts from section 11.4, right? That this goes to 0 for any x. So that was all I intended you to, you've been here, you've been watching what we're doing, so we know that this goes to 0. Now if you want a standalone argument, if you want to justify that, right? Here's a way you could justify it. Here's a standalone argument. So that was basically my initial argument would be by section 11.4 and our previous discussion, right? That's actually what I intended on the quiz yesterday. I was hoping that was your thinking. You just knew that this is one that goes to 0 because n factorial wins. But suppose you didn't know that. What's a standalone argument? How about this? If x is a real number, right, then there exists some k in the natural numbers, right, such that the absolute value of x is less than or equal to k. Do you agree? Wherever you are on the number line, right, you can look at the absolute value of x, and you're a certain distance from the origin, right? If you go to the next whole number past that, you're further, right? You can always do that. Agree? There has to exist such a k. So in view of that, you have that 0 is less than x to the n over n factorial absolute value, all right? X could be negative. But if I look at the absolute value, certainly that's less than 0, right? I guess it could be equal to 0 in the case x is equal to 0, right? Fine. But this is less than or equal to k to the n over n factorial. Well, that's pretty nice, because then I can do things with fractions, because that's k is a whole number. I can rewrite this as k times k times k, times k times k times, however many you want to write. And we start out with n, then we got n minus 1, and then finally 3 times 2 times 1, because it's the factorial, right? That's what it looks like expanded out. Now, we're interested in the limit as n goes to infinity, right? So we are free to make some assumption about n being huge in some sort of way. I know only 7% of you really understand that, but that's okay. So that was a Donald Trump joke. If I have to explain it, though, I don't think it really works. It's too early. Maybe, I don't know. Anyway, so if n is greater than k, just assume this, all right? It's reasonable to assume. We're trying to calculate the limit as n goes to infinity, right? And the Squeeze theorem doesn't say you have to have some truth for all n. It says that if you have an inequality for the tail of the sequence, for the sequence way, way on out, that suffices. So I can certainly choose n to be greater than k. If I do that, what does that give me? 1 is greater than what? K over n, right? And what if I, let's see here. Oh, if I got turned around on this again. Did I do that right? I think I may have did that wrong. What is there? No. I have problems. Just a second here. What can we say about like k over n minus 1? Right. Oh, how about, can I replace this with, I'm sorry guys, I have some mental block all of a sudden. K over n, can I do K over K? No, I don't guess I can do that. No, I can't do that. Oh man. Oh, I tricked myself before class. I was writing up a solution, trying to write, I was working through it fast, and I think I turned an inequality over in my thinking, and I think I deceived myself. So let's take a step back here and think about what we can do. I don't think that's going to work. I mean, what did we have? We had, how did it go? I'm trying to remember that homework problem you had. What did we prove? What was it, 4? Remember that we proved 4 to the n over n factorial was, what was it? Was it this 4 to the n over n factorial was less than or equal to, what was it? 4 to the n over, what I can't, oh guys, you gotta help me out. What was it? What was that? I can't remember. So the logic we used in the solution of that problem to justify that inequality should be, we should be able to like replicate that here. But the thing that makes it harder is that we're doing it for k rather than for 2. Yeah.
For that inequality, you can set it smaller than k to n plus 1 over n.
K to the n plus 1 over what? Over n, you say?
Yes, and that symbol. Factorial.
Well, yeah, but that if I okay, but I mean that's what I'm starting with.
Yeah, and I think we should set k larger than n plus 1.
I mean, if I have this pattern here, right? So basically, this homework problem has k equals to 2, right?
Yeah.
So if we could replicate the arguments in the homework problem here, then that would give us, but you know, anyway, I'll tell you what, guys, I'm going to take a step back. I'm not going to try to do this right now. I'll write the solution up. You can look at it. But we need to go on. I still need to show you some more improper integration. So if I burn 30 minutes in this, then it will be a poor use of class time. The fact remains, though, that we know it goes to 0 by section 11.4. This is a theorem for us. You see why it's important to have as a theorem, by the way. Is for arbitrary x, this is really kind of a pain to work out. Again, I need to just think about the right way of canceling factors to leave myself with something like k to the 2k over n. Oh, wait a minute. I think I see it now. These numbers are all larger than 1, right? So this is less than k over n times k over 1, right? So just what I did was just these guys, right? I'm assuming that n minus, and I think this is what you were trying to tell me a second ago. What was your name in the back?
Me?
Yeah, you.
Hoy.
Say again?
Hoy.
Hoy?
Yeah.
Okay. Tran. Wait a minute, so I've got two trans. Well, this is very confusing. Yes. So n minus 1 is what? We're going to say it's what? What do we need? Smaller than k? Larger than k. So we should assume that n is greater than or equal to k plus 1, let's say. That's certainly a demand we can make on n because we're interested in the limit n goes to infinity. I was about to cut and run on this, but I think we rescued it. So this, I have a fraction where the numerator, given this condition, right? Given this condition, every one of these fractions is some number smaller than 1 because I'm dividing by a larger number, right? So I can replace those with 1 times 1 times 1 times 1, right? And that makes the whole expression, larger. But then you have k squared over n, right? And then by the squeeze theorem, we're done. See, because 0 goes to 0, and k squared over n goes to 0 as n goes to infinity. Therefore, the absolute value of x to the n over n factorial goes to 0 as n goes to infinity by squeeze theorem. And then what's our concluding thought? Hence, x to the n over n factorial goes to 0 as n goes to infinity, right? Because we have this other theorem that says if the absolute value of a sequence goes to 0, then the sequence also goes to 0. That's special to the number 0, right? We had a homework problem where if you had the absolute value of a sub n goes to something other than 0, it doesn't imply that the sequence goes to that other thing, right? Like you can have the absolute value of a sub n going to 1, and it could be that the sequence itself doesn't converge. Standard example being the sequence that oscillates 1 minus 1, 1 minus 1, 1 minus 1, 1 minus 1. There the absolute value of the sequence constant, and yet the sequence does not even converge. Previous homework problem. All right. Sorry that took me so long. Let's go on here. Any questions about this? But you can see how you could get kind of stuck on the logic here, and it's nice to know this as a result that you can use, right? If I said justify this, either you'd use the kind of arguments that are in the book in section 11.4 we went over before, or some kind of hand-to-hand combat like we just did here, right? A critical step in all that is this recognition that you can find a positive integer which is larger than or equal to the magnitude of any real number. That's an important trick, let's say. E, we have n squared plus n to the 1 over n. All right, so what you do here is we're going to say that this is equal to the exponential of the natural log of that thing, right? So if I'm calculating the limit as n goes to infinity of n squared plus n to the 1 over n, well, that's going to be equal to the exponential of the limit as n goes to infinity of 1 over n times the natural log of n squared plus n. Doing what? Doing so that's by continuity of the exponential and the properties of logarithms. Then what? And by the way, a lot of you got this one. I was happy. I mean, I think there's quite a few of you who got that this was 1. But I wonder, those of you who got that I didn't look. I didn't tried to look into your heart and see what was there. I did not try to search your thoughts. I just looked at the number 1 and I put a check. That was the sum total of my grading. So don't, if you got 1 for the wrong reasons, I wouldn't have noticed. Okay, so, check yourself there. We call this thing star, right? And so we got what? Limit as n goes to infinity. Rewriting it a little bit. That's the natural log of n squared plus n divided by n, right? We do L'Hopital on that, extending n continuously. That's infinity over infinity, type infinity over infinity. So I've got the limit as n goes to infinity of 2n plus 1 divided by n squared plus n, all divided by uno. Let's see here. I just extending n continuously. Now that's a very silly fraction to write, right? This is just what? How do you resolve such a limit? Yep.
Divide everything by like n squared.
Right. Pick the highest power that appears in the top or the bottom and divide both by it. Of course, I think if you've been kind of keeping score here, you can come up with some like more heuristic rules, which is what? If the net degree of the denominator is strictly larger than the numerator, it goes to 0. If the net degree of the numerator is strictly larger than the denominator, it goes to infinity, or minus infinity, depending on the sign of the leading term. If the degree of the numerator and the degree of the denominator is equal, the ratio of the leading terms is the limit. This is what we're always justifying by going through this dividing by the top power, and then using the result that 1 over n to the any positive power goes to 0, which we derived from a careful epsilon argument. Yep.
Why can't you do L'Hopital's rule? Because it's like at the last step there, instead of dividing by n squared.
Why didn't I do L'Hopital's rule?
Yeah.
Oh, you could. You absolutely could. Sure. Oh, yeah. I know it's been, it was more the case back when we were doing integration, right? That there were like 13 different ways to do everything. Here, I give the impression there's just one way. It's just because I'm trying to show you one way without I'm just trying to show you one path. Once your eyes open and you see what's around you, you'll find that the path is much broader than I'm portraying it. But I am trying not to overwhelm you guys with jibber jabber about other ways to do things. But that said, now that you've tempted me, I will succumb. And you're right. I do kind of like that way of thinking. This is 2n, right? So that is easier if you're comfortable with it.
Would it be 2 over 2n plus 1?
Ah. But still obviously 0, yeah. I fine. If I'm going to be...
No, I put 0 down and marked wrong, so I was wondering.
Oh, I don't know. It could be. I was grading that pretty fast. You can show me after class. I might have graded you wrong. Oh, yeah. I'm sorry. Excuse me. So this is 0, which is not the end. You take that, find a different color marker. Well, not you guys, just me. But yeah, L'Hopital's rule is also nice. Honestly, by the time you leave this course, when you're faced with a rational sequence like that, I'd really like you to just be able to look at it and write down the answer, frankly. But if I asked you to justify it right now, we go through these sorts of steps and argue by limit law. But I can't bear to write down by limit law. I mean, I'm being. If you want to be legalistic, you could put me in purgatory or something. I don't know. But where was I? Oh yeah, I just need a quiz. Any quiz. All right. Where are we? F. Trying to wrap this up here. We still have other stuff to do. F. Cosine n squared plus 8 divided by n squared. This is like your quintessential squeeze theorem kind of problem. What you do is just minus 1 less than or equal to cosine of n squared plus 8 less than or equal to 1, which implies minus 1 over n squared less than or equal to cosine of n squared plus 8 over n squared less than or equal to 1 over n squared. But plus or minus 1 over n squared both go to 0. Therefore, the cosine of n squared plus 8 over n squared goes to 0 by squeeze theorem. Some of you deceived yourself into thinking the limit didn't exist by doing the following thing. What you did, some of you, a few of you, you did this. You said, well, the limit as n goes to infinity of 1 over n squared times the cosine of n squared plus 8. You're like, well, that is really the limit as n goes to infinity of 1 over n squared times the limit as n goes to infinity of cosine of n squared plus 8. Now, you may not have written this, but you thought this. And why can't you do that? Well, I guess if you did that, you'd still be right here. But you got lucky. We shouldn't do that here, because one of those limits doesn't exist, right? The cosine, this limit right here, this does not exist. So this way of thinking up here really is very dangerous. It can get you into trouble. So I would discourage you from doing that. Although I may have still checked you, because you could have still got 0 even if you made that wrong idea, right? And then finally, two more. F. How long is this quiz? G. So what do we got? We got natural log of an over the natural log of bn. So by L'Hopital's rule on type infinity over infinity, I'm extending n to be continuous. Right, so L'Hopital's rule, I've got a over an divided by b over bn. About 10% of you deceived yourself into thinking it's a over b, but you forgot the inside function's an. So you have to divide by an, but you also have to multiply by a by the chain rule. The a's cancel. You get what? 1. So this goes to 1. It converges to 1. Can you guys tell me a reason that that's totally unshocking? That the a and b don't matter? No, more basic. It's that ln of a, this is really ln of a plus ln of n. Oh, maybe it is what you're just saying. Yes. I'm sorry. I shouldn't dismiss that. So, but that I was thinking a different way. I was thinking after I apply L'Hopital's rule, they're constants, so they differentiate to 0. An alternative way of looking at this would be, as n is huge, the natural log of a or the natural log of b is insignificant. So eventually it's just like log n over log n, which is obviously 1. Asymptotically it goes to that. But anyway, either you do the chain rule or you use laws of logarithms. Either way, there's no A or B dependence, even though it appears there might be. Questions? Okay. And then finally, H, we have, what is it, n squared e to the minus n. And again, I'm going to L'Hopital. Oh, not yet. Oops. This is equal to n squared over e to the n, right? By the way, it's one of the things I would try to come to as I'm studying is just some basic rules of thumb. One of those basic rules of thumb is, as I mentioned before, the exponential wins, right? In a battle of power function versus exponential wins. In a battle of factorial versus exponential, factorial wins. So of course factorial also beats power functions, right? It's kind of the pecking order. If you multiply these things by natural logs, well then it gets complicated. Anyway, so this is by L'Hopital's rule, extending n to be continuous on infinity over infinity. What we got? We got 2n over e to the n, and then you L'Hopital it again, right? And you get 2 over e to the n, which goes to 0. So therefore, the limit, as n goes to infinity, of n squared e to the minus n is in fact equal to 0. As I've warned you, I'm very picky about the definition of the limit. If you have an x there, there's something wrong. I'm not going to belabor that point further, but you do need to finish memorizing it, basically. All right. So that brings us finally back to what? Improper integration. What was the example that we started but didn't finish yet? So I had said we should find k such that f of x is equal to k times the inverse tangent. Oh, I'm sorry. Idiot. K over 1 plus x squared is a probability distribution. What's a probability distribution? So all that means is that the integral from minus infinity to infinity of f of x dx is equal to 1. So what we have to do is we have to do the integral from minus infinity to infinity of k dx over 1 plus x squared. Now, how do you define such an integration? Obviously, the bounds are improper, right? They're infinity and minus infinity. That's pretty obvious. It's in our face. And then you might worry about, we have division in the formula, right? So division by 0 is always problematic. Natural log of a 0, problematic, right? But here we got division, but this is not problematic at all, right? Because 1 plus x squared is what? On its worst day, it's 1, right? It's usually bigger than 1. So no problem, right? So the only thing I have to worry about in terms of improperness is just the bounds. So by definition, you can split it wherever you want. So if you think about this geometrically for just a second, 1 over x squared looks something like this. So this is representing the area under the whole curve from plus to minus infinity. Basically, you can split and say the left area plus the right area wherever you want. For me, it's just convenient to do it at 0 for this one. But you could just as well split it over here if you wanted, or over, I mean, wherever. You gotta pick some point. So I'll pick 0, minus infinity to 0. Okay, and then what? Then you go back to the definition. This is the limit as, let's say, a goes to minus infinity of the integral from a to 0 of k dx over 1 plus x squared, plus the limit, let's say b goes to infinity, of the integral from 0 to b of k dx. Now, I used a and b here. You could just as well use any other letter you want. I mean, it doesn't matter. You could put a Pac-Man here, and there'd be Pac-Man up here, right? You could put a ghost, I don't know, whatever. Doesn't really matter what you call these things. I'm just calling them a and b because we often talk about integrals from a to b, you know? But that's by no means, you know, it doesn't matter what letter you use there. Just don't use x. One letter you cannot use is x. The other letter you can't use in this problem is k. K would be a bad choice, okay? Oh, sorry about that. All right, so this is the limit as Mr. Ghost here, I regret this, goes to minus infinity of k times the inverse tangent of what? Of 0 minus k times the inverse tangent of Ghost. Plus the limit as Pac-Man goes to infinity of k inverse tangent of Pac-Man minus k inverse tangent of 0. You see what, okay, so like what would have happened if instead of splitting it at 0, I'd split it somewhere else? Just hypothetically, just think about that for a second here before we, that's what I want to talk about why it doesn't matter where you split it. In the calculation, right? The next step you're going to do is like fundamental theorem of calculus, right? Part 2 done twice. In the integration on the left, you're going to have like something like plus the antiderivative at the splitting point. On the antiderivative of the right half of the area, you're going to end up with like minus the antiderivative at the splitting point. The splitting point happens to be, I chose it to be 0, right? And it's true that the inverse tangent of 0 is 0. But even if I'd done this at somewhere else, like here, you know, suppose I'd split it at a, I would still have just had, you know, like an a inverse tangent of a here, an inverse tangent of a here, and they would have canceled. So it's immaterial where you split the integral from minus infinity to infinity. You'll end up with the same answer. It doesn't matter where you split it. So we just split it at 0. And that makes this go to what? That's 0. This is 0. These arrows are not limiting arrows. Those are just equal. It's really equals to 0 if you don't. And then how about this? The inverse tangent. What happens to the inverse tangent as we go to minus infinity? By the thing I just erased here. Negative pi over 2, right? So this, man, I want another color. So we got minus pi over 2 from the one. We got pi over 2 from the other, right? This tends to pi over 2. Minus minus gives me plus, so I've got what? I've got k pi. I want this to be equal to 1, right? So therefore, I choose k is equal to 1 over pi. That is, so f of x equals to 1 over pi times 1 plus x squared is a probability distribution. the area it bounds under the under its graph for all x is 1. Thank you. Your homework is cramping my style. I mean, it makes sense. That's a very good way of organizing homework. I would not have thought of that. That's smart. So now he, in section 11.7, he has a laundry list of examples that he does for us. The major one being the study of the integral of dx over x to the p. We also have a comparison test and a discussion of what it means for an integral to diverge. Okay, and that's about it. So there are really two major theorems per se in this section, and just terminology, convergent and divergent. All right. So I need to talk about the comparison test, obviously. Let me do that. So the idea of the comparison test is very, very simple. If you have two continuous functions from, say, a to infinity, all right, step number one. And we have an inequality which relates them, that allows us to compare them. In particular, we have 0, right, is less than or equal to f of x, is less than or equal to g of x for x greater than or equal to a, all right? Then we have two conclusions. One, if the integral from a to infinity, all right, of g of x dx converges, what does that mean? Right, that means that if we calculate these integrals, this integral converged. Actually, both the right and the left one separately converged, as it happens to the same value, k pi over 2, but that's coincidental. So converge just means that when you calculate the limit that's implicit within the improper integral, it converges in the sense of limits converging. If that limit doesn't exist, we say that the integral diverges. So the convergence or divergence of the limit is then bestowed upon the integral. That makes sense? So if this converges, then what do you think? Yeah, f of x also converges. Does that make intuitive sense to you? I think it makes a lot of sense if you think about it, right? If something larger converges, certainly something smaller must also converge, right? If the area under g of x is finite, going out to infinity, then surely the area under f of x must also be finite. That's easy enough to write down and to understand. It's probably also not that hard to prove. The harder part here really is applying it in creative ways. So if, on the other hand, the integral from a to infinity of f of x dx diverges, which is just fancy speak for doesn't converge, then what? the integral from a to infinity of g of x likewise diverges. You don't have to put the likewise there if you don't want. In fact, what does it diverge to? If you look at this, what are your choices here? Well, we're talking about positive functions, right? So what's it going to diverge to? What? 0? No. In fact, we'd say this is equal to infinity. And this one would also be infinity, the whole thing. Not the integrand, but like the whole thing. He doesn't have that in, this is theorem 11.7.2. He left the proof as an exercise. And that's fine. Yeah. Really, the proof of this is nothing more than, remember you guys asked me that question about an integral, and I mentioned to you if you have m times b minus a is less than the integral from a to b of f of x dx is less than or equal to the big M times b minus a. Remember that? So if you have bounds on the functions, you can bound the integral between basically the length of the integration region times the lower bound and the length of the integration region times the bound above. So essentially, if you use that inequality property for definite integrals plus the squeeze theorem, which is known for limits at infinity, put those two things together, you get this theorem. It's really just that. So let's see here. Something we could do right off the bat. How about this? If I had the integral of, I don't know. Let's say dx over from, say, 0 to infinity of, like, I don't know, x squared plus 3x plus 1. Does this converge or diverge? Surely this is less than or equal to integral from 0 to infinity of dx over x squared plus 1, right? And so this right here, what I'm doing is I'm saying, well, 1 over x squared plus 3x plus 1, right, is less than or equal to 1 over x squared plus 1 for x greater than or equal to 0, right? So you can apply this theorem in the case that what? The case that this diverges. I mean, in other words, I forgot the punchline. There's a stronger theorem than just this, though. By the way, it's that the integral from a to infinity of f of x dx is in fact less than or equal to the integral from a to infinity of g of x dx. I mean, you get more than just convergence. You actually can compare the values to which they converge. It's a comparison theorem. So starting with this example, right, we just worked this one out. We figured out that this is equal to pi, right? So I know this thing is equal to pi. If it equals to pi, it certainly converges to pi. So that tells me, in fact, that this integral over here is likewise convergent. Now, I can't say it converges to pi. I don't know what it converges to, but I do at least have in my possession the statement that it converges. Do you see that? So this theorem doesn't tell you what they work out to, but it does at least tell you yay or nay, it converges or diverges. So in order to use a comparison theorem effectively, what you need is what? You need something to compare to. So this is one example to compare to, but are there others? Fine. So this arrow here is the